Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss one of the transport phenomena, that is diffusion, means transport of mass. Let's begin. Diffusion we may describe as the transport of mass resulting from random molecular motion and takes place whenever there is different molecular concentration in different parts of the gas. In such a case, a more denser region will lose more molecules to the regions of lower density to bring the equilibrium state. This phenomenon is called diffusion. The transport phenomena means the not equilibrium state, the states which are not equilibrium that transformed to equilibrium state. In this case, in diffusion means transport of mass, there will be the flow of density to lower denser region, the flow of masses from denser region to lower denser region, means a more denser region will lose more molecules to the regions of lower density to bring the state in equilibrium state. This is the process, we say that is the diffusion process, and the phenomena of diffusion we can explain on the basis of kinetic theory of gases, considering the transport of mass across a given plane. And the diffusion is the movement of particles. Here the diffusion is the movement of particles from one area of higher concentration to an area of lower concentration until unless evenly spread out. So, that is the transport of mass and the phenomena of diffusion. Mathematically, we derive what process occurred throughout that diffusion process, means the transport of mass process. Here we consider let us consider a mass of gas moving in parallel layers. As you take the planes, O, X, Z direction. This is the parallel layers as A, B, C, D, L, M. We consider the mass of gas is taken into consideration between the parallel layers AB and CD. Let here we take LM is the intermediate plane. This is the intermediate plane. Suppose the concentration increases. Concentration means the number of molecules per unit volume, that is the concentration. Concentration that is the number of molecules per unit volume. Here the concentration increases in the vertical direction, means as we proceed from AB to CD, then the number of molecules per unit volume, that is the concentration, will increase. Thus, the concentration of gas, there will be the gas on the above of AB, on the above of LM plane, the below of LM plane. So, here the concentration is increased or high as comparison to that of lower portion of LM. The concentration of gas above that of plane LM is greater that of gas below LM. Here the concentration of gas, here the concentration is high, here the concentration is low, concentration is low. Here means the upper region of LM plane, the gases or the number of molecules per unit volume is high, and below that of LM plane the concentration is low. In order to bring the equilibrium, means there will be the difference of concentration between the upper and lower regions of that of plane LM. So, in order to bring that equilibrium, the molecules of the gas due to thermal agitation will move from the plane CD to AB, crossing the plane LM until the concentration in every region is same, till the movement occurs from CD to AB through LM, until and unless there will be no such equilibrium state is achieved. Thus, the phenomena of diffusion may be considered as the transport of mass. So, the phenomena of diffusion which is called the transport of mass, due to the difference in concentration between the upper and lower regions of LM, the molecules are moved from CD to AB through LM until and unless we get the equilibrium state. So, we can mathematically derive the coefficient of diffusion. Let here we take, let concentration at the plane, is equal to small n. Concentration at the plane LM, here we take the plane LM as n, the concentration here will be n, and the rate of change of concentration with distance in upward direction perpendicular to that of plane LM is dN by dz. The rate of change of concentration with distance means which is known as the concentration gradient, that is the concentration gradient in upward direction which is perpendicular to that of plane LM, perpendicular to the plane LM is equal to, that is dN by dz. Then what happened? And the distance between each planes means AB to LM and CD to LM, that distance is the lambda, which is the mean free path. Distance of each planes AB and CD from the plane LM is equal to lambda. Then concentration at the plane CD means N plus lambda times dN by dz. This is the concentration at plane CD, and here the concentration at plane AB, that is N minus lambda times dN by dz. The concentration at plane LM, concentration of the gas molecules at plane CD, concentration of the gas molecules at the plane AB. Then we write all the things. Concentration at plane CD is equal to N plus lambda times dN by dz. Concentration at plane AB, that is N minus lambda times dN by dz. Now the number of molecules from the plane CD crossing the plane LM downward per unit area per second is equal to, here look at one thing, as the molecules are moving in all possible directions due to that of thermal agitation, it may be supposed that 1/3 of the molecules are moving in each of the 3 directions which is parallel to that of Cartesian axis, 1/3 of these molecules. So that on an average, if we take on an average, that means 1/6 of the molecules move parallel to any axis in one particular directions. 1/3 of the molecules move each of the 3 axes parallel to Cartesian coordinates, but on an average 1/6 of the molecules move parallel to any one of the axes in one particular directions, as we have discussed in case of coefficient of viscosity and coefficient of thermal conductivity in previous 2 video lectures. So here that concept is used. The number of molecules from the plane CD crossing the plane LM downward per unit area per second, that is 1/6 into c bar. C bar is the average velocity, n plus that term, that is lambda dN by dz. Here c bar is the average velocity. Due to thermal agitation. Similarly, the number of molecules from the plane AB crossing the plane LM upward per unit area per second. Similarly, right here the number of molecules from the plane AB crossing the plane LM upward, this is the downward, this is the upward, per unit area per second is equal to, again that is 1 by 6 times c bar into n minus lambda dn by dz. This is the number of molecules passing to the top plane Lm downward, using that equation as concentration at plane CD, and again the number of molecules from the plane AB crossing the plane Lm upward per unit area per second, using that concentration term here, that equation. Now what should be the net number of molecules passing? So here the net number of molecules, hence net number of molecules crossing unit area of the present Lm, unit area of the present Lm or Lm plane per second is equal to, the net will be E, that is the difference between these two, 1/6 c bar n plus lambda dn dz minus 1/6 c bar n minus lambda dn by dz. On simplification we have 1 by 3 c bar lambda dn by dz. Now we define the coefficient of diffusion. Therefore coefficient of diffusion D. We define the coefficient of diffusion is the ratio of number of molecules crossing unit area per second, to that of concentration gradient. Here the number of molecules crossing unit area per second, it is 1/3 c bar lambda dn by dz divided by concentration gradient dn by dz. That term cancel out. We have 1 by 3 c bar lambda. Let me multiply rho in the numerator and denominator. We have 1 by 3 rho c bar lambda divided by rho. There will be no such change. Rho be the density. Rho is equal to density. 1/3 rho c bar into lambda, that term is equal to the eta, and the coefficient of viscosity eta is equal to 1/3 rho c bar lambda, which is the coefficient of viscosity, eta by rho. D is equal to the coefficient of diffusion. D is equal to the ratio of coefficient of viscosity to density. Look at that equation. Since we know lambda is directly proportional to, inversely proportional to the number of concentration and the number of molecules, and again that is proportional to T by P, temperature, absolute temperature, P be the pressure, and the average velocity directly proportional to the under root of temperature. Overall, from these equations we have D is directly proportional to the coefficient of diffusion is directly proportional to, that is T to the power half, that is T to the power 1, that is T to the power 3 by 2, where T be the absolute temperature. This is the mathematical expression for coefficient of diffusion. So, with the help of this visual expression, we understand what is diffusion, means the transport of mass. This is the diffusion phenomenon, and mathematically we derive the equations related to diffusion of gases. So, here we consider all these things and mathematically derive the coefficient of diffusion. The coefficient of diffusion D is equal to eta by rho, and finally that is directly proportional to T to the power 3 by 2, T be the absolute temperature. So, with this useful and informative notes, let me wind up this session. Thank you.